Hey everyone, I'm going to discuss this topic, which is K-means clustering with incomplete data using Mahalanobis distance. So this is based on a paper which was published by authors Lewis and Igor, uh, which was published in archive uh, paper on November 5th, 2024. So what is K-means clustering? Basically, it is a unsupervised machine learning algorithm used to group unlabeled data into a cluster based on the similarity in the data points. Uh, the applications which were mentioned, clustering has many applications in many fields, but mainly discussed in the paper where computer vision, it has the image processing and security, where it can detect DDoS attacks, and in the health and social science, it is used for data summarization, segmentation, and there are many applications in general. How does it work? So what we have is we have the cluster. We are giving a initial k value, and it is randomly selecting k initial centroids in the cluster, and then it is assigning each data point to the nearest centroid based on Euclidean distance, and updates this, and then recalculates the centroid as the mean of all the data points which are assigned in each cluster, and it is going over and over again, iterating again, and this repeat the assignment and updates steps until the centroids no longer change or the maximum number of iteration is reached. So here we can see, this was the cluster. It has first taken this triangles as the centroid, and then it has just plotted this, and then the centroids are changing. Next we have is the limitations which k-means clustering is having. So k-means clustering is sensitive to the initialization. The k-means algorithm is highly sensitive to the initial placement of cluster centroids, which can lead to inconsistent clustering results, or even failure of converge to the correct number of clusters. Euclidean distance limitation. So traditionally, k-means uses this method to calculate the distance between two data point, which may not be very well suitable for non-spherical clusters. So this will work fine as long as the dimensions are equally weighted and are independent of each other. That means there is like no correlation between the data points with the centroid, and the limitation can lead to poor clustering performance, especially when data exhibits elliptical shapes. And there is one more thing, like handling the missing data. Standard k-means struggle with the incomplete data set, often require imputation steps that can distort the data distribution and reduce the clustering effectiveness. So the proposed solution discussed in the paper was, there was a unified approach discussed, where the method integrates the imputation and the clustering into a single objective function, enhancing the clustering performance for dataset with non-spherical clustering clusters. This there is so Replacing the Euclidean distance, there is this Mahalanobis distance, which is basically distance between a point and the distribution of the cluster. By utilizing Mahalanobis distance instead of Euclidean distance, the algorithm effectively manages elliptical cluster shapes, which are often challenging for traditional k-means clustering, accounts for covariance structure, enabling clustering for elliptical shaped clusters. How does this work? So we have this formula for Mahal distance. D square is the square of the Mahalanobis distance. This x is the vector of the observation. I mean, that is the one data point, and m is the vector of mean values of the independent variables. So mean of all data points, and C is the covariance matrix of independent variables, which is like the inverse of covariance matrix we are using. So the step-by-step approach of this proposed algorithm is we are initializing centroids from a complete data point and estimating the covariance matrix. Iterative process, update the assignment matrix based on the Mahalanobis distance, recalculate cluster centroids and covariance matrices, impute missing values using conditional means as the algorithm processes, and converge repeat the process until the change in the objective function falls below a specified tolerance level. So either the number of iterations are over, or again it is giving same centroids. So what they have done is they used iris dataset, which is a standard dataset for like a very common famous dataset for clustering and other operations, machine learning algorithms. So we have a 150 sample and 4 dimensions and 3 clusters in it, and then they have generated a synthetic dataset containing 1000 samples, 5 dimensions and 10 clusters. So what is happening is they have removed some percent of the data, uh, 10, 20 to 50% to be exact, and 50% data from 1 or 2 coordinates. So they have 4 dimensions, out of which first they have tried removing 10%, 20, 30 and 40, 40 and 50% from one dimension, and then same from the second dimension. This approach allows for comprehensive evaluation of the algorithm under different level of data incompleteness. And evaluation matrices metrics are the performance of the clustering algorithm was assessed using adjusted rand index and normalized mutual information. These matrices, these metrics quantify the similarity between clustering results and true labels, providing insight into the effectiveness of each method. So what was the finding? We had for the one coordinate missing values, K-Mahal consistently outperformed unified k-means, which is k-means with imputation, and k-means across various level of data incompleteness. At 10% data, K-Mahal achieved NMI of 0.91 compared to 0.758 for both unified and normal k-means. And even at 50%, K-Mahal maintained a high NMI of 0.904, whereas the other two were pretty low. And then clustering performance with 2 coordinate missing. At 10%, K-Mahal was having NMI of 0.901, and unified and normal k-means achieved 0.758 and 0.747. And even at 50%, K-Mahal outperformed, where NMI dropped to 9.4. Oh, okay, here we can see like for 50%, K-Mahal has dropped to 0.93, 0.539, but it still outperformed the k-means, unified k-means and k-means cluster. Here we have the table, the entire table. So the ARI trends, the K-Mahal demonstrates superior ARI values across the different level of missing data. For 10% of data, K-Mahal achieved a ARI of 0.978, and even at 50% it has a 0.895. So this is the table which was from the paper. We can see like K-Mahal has when it comes to KNN imputation. So there are different type of imputation used in this experiment, but KNN gave the best performance. And using this imputation method, K-Mahal was always outperforming, and the bracket one is the ARI value. The bracket one is the interquartile range value, and the ARI is always greater for K-Mahal than the other two methods. In most of the cases, and 50% here we can see like it has dropped. But yeah. So the applications was again K-Mahal can be used to cluster patients' data with missing values, enabling more effective patient segmentation and personalized treatment plans. This is particularly important in medical dataset where incomplete information is common due to reasons like patient non-compliance or data entry errors. In finance, K-Mahal can identify customer segment for targeted market campaigns, even with incomplete customer data. This capability allows financial institutions to make informed decision, thereby improving customer relationship management. Image processing. K-Mahal can be applied to image segmentation task where pixel data may be missed or corrupted. By clustering incomplete image data effectively, it enhances image analysis and object detection processes. So the conclusion was the study demonstrated that K-Mahal, which is integrates the Mahalanobis distance with unified approach to imputation and the clustering, significantly outperforms the traditional k-means and the unified k-means algorithm, especially in the scenario with incomplete data. Potential improvement. So we have the example where K-Mahal achieved, as discussed earlier, it achieved greater ARI compared to the other two algorithm. Potential improvements. So in the future, we can have a targeted technique which is tailored for this kind of elliptical clusters for imputation, and it will further enhance the performance of K-Mahal with higher value of missing data. This could involve exploring advanced methods like multiple imputation or regression imputation to better estimate missing values. Broader implications. The findings suggest that the integrating imputation directly into clustering algorithm can lead to more robust and reliable clustering outcomes, particularly in the field where data incompleteness is common, such as healthcare and finance. So these are the references which I just mentioned. Thank you.